We are ready to start. So welcome everyone to Harvard CMSA Quantum Math and Math Physics Seminar Series. We are very delighted to have a Professor Eslam Khalaf based at Harvard University, and he'll be speaking about very detailed and very introductory and pedagogical introduction to this new physics on quantum or to Harvard physics in twist bilayer graphene. So let me remind the audience, please feel free to ask questions and interact with Eslam. Yes, so please.
Okay, thanks, Julian, for the introduction and for inviting me to talk here in the seminar. So yeah, what I'm going to talk about today is mostly some recent unpublished results about kind of our developing understanding of the physics of twisted bilayer graphene, and in particular highlighting some aspect that this system turns out to be kind of much richer than we and most people initially anticipated, in the sense that it really captures a lot of the essential physics of two of the most well-studied, strongly correlated systems, which are quantum physics and the Hubbard physics. So let me start by acknowledging my collaborators. The main driving force behind this project is Patrick Ledwith, who's a grad student here at Harvard. But there's also other collaborators involved. One of them was Chen Li, who's my student who moved here with me from UT Austin. He's here in the audience. So let me start by a very brief review or introduction about twisted bilayer graphene. So I'll not spend a lot of time on the basics of twisted bilayer graphene, but the idea is twisted bilayer graphene is formed when we have two graphene sheets twisted relative to each other by some angle, and when this angle is around the so-called magic angle around 1 degree, we notice the appearance of a pair of very flat bands at charge neutrality. And when I say a pair here, I mean in graphene we have a spin degree of freedom and a valley degree of freedom. So if we look, so we have 4 flavors, and when we look for a single flavor, so per spin per valley, we get these 2 flat bands. So we have 8 flat bands in total. And so there was a theoretical prediction that at this angle we get these flat bands, and flat bands usually mean stronger correlations. Prediction was first done by Bistritzer-Macdonald in 2011. And 7 years later, in 2018, there was a remarkable discovery that the group at MIT, led by Pablo Herrero, actually did manage to make the system and did observe a very interesting correlation phenomenon. So, the first thing they looked at was the conductance of this system as a function of the carrier density, and the carrier density in the system can be easily tuned by gate voltage, because when we form this, we get this very large Moore unit cell, so it's very easy to dope this system by just applying some gate voltage. And what they found was that there are certain fillings, certain carrier densities at which the conductance goes to 0, so we get insulating behavior. And some of these are kind of easy to understand. For example, here is the filling at which the flat bands are completely empty, so we just get a band insulator. And the same here, where the bands are completely full. But they also found that at partial fillings of the band, in particular, a filling of 2 electrons or 2 holes relative to that charge neutrality point, we also get some insulating features. And these cannot be simply explained by band theory. We have to invoke interactions. So these are called correlated insulators. Furthermore, when they looked at a slightly different measurement setup, 4-terminal rather than 2-terminal, they found that actually these correlated insulators are flanked by some superconducting groups. And in the years since then, people have seen all kinds of correlated phases in the system, including quantum full states, orbital ferromagnets, strange metals, and I'll explain this a bit more in detail. And one of the questions that has been really in the discussion since the very beginning was what is the relation between the system and other non-strongly correlated systems. In particular, this kind of phase diagram where we have a correlated insulator at some integer flanked by some superconducting domes bears kind of striking resemblance to one of the most well-studied phase diagrams, which is that of great high temperature superconductors. So the initial idea was that maybe this model is described by kind of very similar physics, which is the Hubbard physics. However, subsequent work have identified that there is a very important feature of this system, which is the band topology, makes it a lot more similar to another system, which is also another very well-studied, strongly correlated system, which is a quantum system. And one important question has been, which of these capture the essence of the physics, or is it somehow some combination of the two? So let me first kind of review what I mean by Hubbard physics or quantum physics. So the Hubbard model is kind of the standard model of strong correlations. And the main idea is simple. The starting point is usually we focus on some band or a set of bands and we forget about the rest. And for these set of bands, we find a basis of localized orbitals. So we find a basis of orbitals where each electron is attached to one orbital that is strongly localized on the lattice side. And when we project the interaction and the single particle dispersion on this basis, we find that the largest energy scale in the problem is the so-called the Hubbard U scale, which is the energy scale that penalizes two electrons from sitting at the same side. And this leads to very interesting physics. In particular, if you think at half filling, so when you have one electron per side, you get a situation where it pays a huge energy penalty for an electron to move from one lattice side to the other, because this leads to double occupancy, which leads to this very high energy penalty. So we find that at relatively large temperature scales, the charge fluctuations are completely frozen. So this is a system where charge no longer fluctuates at a very high temperature scale, but you still have a free spin moment at every lattice side. And this free moments only order at a parametrically smaller energy scale that's usually given by a so-called super exchange scale, which is if you allow the electrons also to hop, where this hopping energy scale is much smaller than the interaction scale, you get in second order perturbation theory a term that's proportional to t squared over u, usually called J. And this gives you some anti-ferromagnetic interaction that would lead to ordering at a much smaller scale than this U scale. So this separation of scales between when charge fluctuations get frozen and when the magnetic order is established is kind of a hallmark of the physics of the Hubbard model. And one of its main, there is kind of several observables that could be associated to it, but one of the main observable consequences is that in this region where we have where the charge is frozen and we may get some kind of insulator, this is an insulator with a very high entropy because the spin haven't ordered yet. So at every lattice side we have this free moment that gives us an entropy that is of order, an entropy of order 1 per lattice side. Of course, in our model, in the kind of standard example, like of the Hubbard model without any extra terms, the spin order is antiferromagnetic, and as I said, it sets at a much smaller energy scale, a much smaller temperature scale. And the Hubbard model is characterized by, it's very well studied. So under some conditions, it can lead to superconductivity, charge density waves, and many other exotic phases, particularly as you go away from this half filling one.
Excuse me.
Yeah.
Is the T here the hopping stress similar to the J in the company?
Yeah, J is T squared over U. So I didn't. Yeah. It's T squared over U. It's what you get in the second order.
And what happens if U and J stress the exchange? Suppose.
Well, if J is roughly the same order as U, then you just order immediate. Like the spin and charge order happen at the same time. So you will not get this region where you have the so-called Mott insulator. So you have an insulator without charge fluctuations, but with a large entropy. So which means spin is still free. So if the two are of the same order, I mean, of course, if T is much larger than U, you're in weak coupling. So there's just kind of a weakly interacting metal or intermediate interacting metal. If J and U are of the same order, then probably you will not have this separation between the charge ordering scale and spin ordering scale.
So if J is larger than U, then this diagram there is no intermediate phase in between.
Yeah, actually, I mean, this diagram is built assuming J is either smaller than U or of the same order. So if J is larger than U, you have a different model. It's a model where there's both where there's some magnetic correlation, but also there's charge fluctuations, obviously, an insulator. So the kind of another paradigm of strongly correlated physics that's really quite different in several important ways from the Hubbard physics is a quantum Hall problem. So in the quantum Hall problem, the main setup is that we subject electrons in 2 dimensions to a very strong magnetic field. So we get these so-called Landau levels. So they are the energy levels in a magnetic field. They are these very flat bands. And here we see that one of the very first assumptions that we use in analyzing the Hubbard problem breaks down because due to the band topology of these Landau levels, we cannot really find the basis of localized orbitals. In particular, there is no basis of exponentially localized orbitals. Furthermore, even if we look at something like the charge density is uniform in this system in contrast to our model where the charge is just peaked. It's almost a delta function at these lattice sites. There is a very important consequence of the fact that there is no basis of exponentially localized orbitals, which is that in this system, we don't really have this separation of scale between spin ordering and charge ordering because whichever way we try to organize some real space some orbitals in real space, these orbitals will have large overlap. And a consequence of this large overlap is that there is a very large so-called direct exchange scale. So direct exchange scale means that the wave function, because the wave functions are overlapping, they are actually trying to ferromagnetically order at the scale that is of the order of the interaction scale. And one simple way to understand this is this is really what leads to Hund's rule in chemistry. So usually Hund's rule tells you that if you try to fill some orbitals with some electrons that could have spin up or spin down, that they try to fill to order ferromagnetically so that all the spins have the same spin. And the reasoning is that if these orbitals have spatial overlap, then the wave function has an orbital piece, spatial piece, and a spin piece. And if the spin piece is fully symmetric, then the orbital piece is fully antisymmetric. And being antisymmetric means the probability of 2 electrons being at the same site or the same region of space is reduced, and this minimizes the repulsive energy. One kind of interesting feature of the quantum Hall, of this ferromagnet that forms in quantum Hall systems is that there are non-trivial ways to introduce charges in the system. In particular, you can form these fermion textures, and fermion is just some topological texture that you can form in any ferromagnet. But in the case that this ferromagnet is also a quantum Hall system, these textures turn out to carry a charge. So they carry an electric charge that is equal to their their winding to the winding number of this Kermian texture. I mean, this is not. This is a topic I'll just touch very briefly, so it's not. It will not be the main part of my talk. There's also very interesting, of course, and famous aspect of the quantum mode physics, which is that we have these fractional phases. If we fractionally fill one of the Landau levels, due to interaction effects, we get these phases that has fractionally charged quasi-particles that are neither fermions or cold anyons. One interesting aspect of the quantum physics that is kind of unique and definitely is very different from the Hubbard physics is that its description actually has a UV-IR mixing, and this comes from the following observation, that if you take the position operator and project it onto a Landau level, the X component and the Y component don't commute. Instead, they satisfy this kind of Heidelberg algebra. What this means is that the Y component can be understood as the momentum conjugate to X. So small distances in X map are related to long distances in Y, and vice versa. So short and long distances are mixed, and also momentum and real space are dual to each other. So we see that although these two are strongly correlated systems in the sense that the interaction scale is the largest energy scale of the problem, their phenomenology is quite different. And one of the, for example, in our model, you get antiferromagnetism, and here you have ferromagnetism. But also the other very crucial distinction between the two is that in the Hubbard model, there is a separation between the scale at which you get charge ordering and the scale at which you get spin ordering, while here they would happen at the same time. Because this exchange scale is just governed by the interaction scale. There's actually no other scale in this.
Actually, sorry, just make sure. Remind me, the skirmion is which homotopy group? There are some related.
S2. S2 of S2. So you compactify the plane into a sphere, and you look at pi2 of S2 because the order parameter is also used.
Okay, but this will be a Z class.
Yeah. So you can have winding number is an integer, and the charge is equal to basically the winding number times the Chern number.
But I remember there are relation between skirmions to H-Pop, which is more like it's more like a configuration of something with singularity at the space-time one point.
Yeah. So in 2+1, I think hedgehog is going from a skirmion to an anti-skirmion. And then you'll have a singularity in the middle.
But that's a kind of symmetry breaking kind of this orders or something.
No, this is a quasi-particle. So I think in any ferromagnet you can form a skirmion, and it has some stability as a quasi-particle because it's just because it has topological stability. But then the new thing or the interesting thing is if the ferromagnet is a quantum Hall ferromagnet, then the skirmion is a charged object. So usually it would be a neutral object. It will just consist formed out of spins. But in quantum Hall systems, there is a subtle commutation relation between the charge operator, the density operator, and the spin operator. And this means when you form a texture in the spin, you actually could get a finite charge. And I mean, if you want to think of it microscopically, you can think that in quantum Hall systems, the spin flip actually carries a dipole moment. So if you add a charge, it would attract to it a lot of spin flips, and these spin flips, the kind they want to organize is in this skirmion texture. So energetically, this is kind of the microscopic reason why you get these skirmions on quantum Hall ferromagnet. But in the field theory, it's just because you get a topological term that ties the electric charge to the winding of this field.
Some symmetry has to break.
So this is a ferromagnet. So we have a ferromagnet that already broke some symmetry, and then we form the skirmion as a texture on top of the ferromagnet. So which symmetry do you mean?
Ordinary, for instance, in 2D materials, the inversion symmetry is broken. So therefore, you can form these sort of chiral interactions which lead to
So here, I mean, it's a quantum Hall system, so time reversal symmetry. And this is what gives you the chirality of the texture. But yeah, it's true. So to get this term in the field theory, you would need to hear the breakdown reversal.
Was coming also break SO3 if the spin oriented in some way?
I mean,
If there's
it forms on top of a state that broke SO3 spontaneously, and it's that. So in this context, you think of it as an excitation on top of a symmetry broken state. It's like what you think of a vortex in a superconductor. So it's not the same because there's a finite energy excitation vortices are as logarithmic energy.
Can you like yeah, we can go back one slide, just maybe summarize in a sentence. It's like it's an interplay between symmetry breaking ferromagnetic order affects the statistics of some conventional-like states. How does that work out? Just
well, which part are you? So you're talking about the ferromagnetism. If you have a ferromagnet and you form a skyrmion,
yeah,
then the skyrmion carries charge E and it is a fermion.
Okay.
And the reason it's a fermion is because you get a half term in the field theory. So this is how the background Chern number actually does affect the statistics of the object on the field theory level. Yeah, and if it's Chern 2, like if these bands have Chern number 2, then this would be a charge 2 skyrmion. Then the skyrmion that has the simplest winding has charge 2, so they're all bosons. So depending on whether the Chern number is even or odd, the simplest skyrmion could be either boson or fermion.
And how the anions show up here?
No, anions is a different story. So I mean, so there's kind of, I'm here kind of reviewing all the kind of things that could happen in a quantum Hall system. So one thing is if you take a quantum Hall ferromagnet, which means that you take a quantum Hall system like SU2, so there's 2 levels, and you're half filling. So then you get a ferromagnet. But then you can also ask what happens if I look at only one of these. Let's say this, I already formed this, but then I want to fill this one, and then I get lofted state or some other kind of topologically ordered quantum Hall state. So these are kind of 2 different aspects of it. One is at integer fillings and one is fraction filling. Yeah.
One more question. So the students are always excitations. They are never for any system the ground state, is it?
Well, they are excitations in a certain charge sector. So that's if you say what is the ground state of this system at the filling of 1/2, like 1 electron per side plus 1 electron in the whole system, so 1 charge. As you had 1 charge. It could be that the ground state could be a ferromagnet plus a skyrmion, because but it's the ground state in a given charge sector. Of course, it's an excitation in the sense that the ferromagnet is lower in energy than the thing that has the texture. But if you think if these are not charged objects, then of course the skyrmion is always an excitation. Well, unless you get a skyrmion crystal or something, but skyrmion is always an excitation.
Technically, they're always excitations.
They are always excitations, but of course here you have a conserved quantity which is a charge, and if you look at the given charge sector, this could be the cheapest, the lowest energy state.
So there are 2 different physics, and you are not going to mix them together.
Well, actually, the skyrmion part is kind of a very minor part of the whole story because it's part of the older story that's more kind of a quantum Hall. Now I want to discuss more how you reconcile this with the Hubbard physics. But the idea is, of course, so in these systems like twisted bilayer graphene, the filling is a continuous variable. And and you have these flavored degrees of freedom. So if you're at integer filling, the relevant physics is that of ferromagnetism. Then if you go very slightly away from integer filling, the relevant physics is that of few excitations on top of the ferromagnet. So the skyrmions could be relevant there. But then if you had like a 1/3 filling of 1 Chern band, then the relevant physics is that of fractional quantum state. So this is kind of a review of all the kind of stuff that happen in quantum physics, and then you'll see that many of these are relevant also. So in twisted bilayer graphene, if you just look from a phenomenological point of view, you'll actually see that there is a lot of features, or there's some features that can be more naturally explained in terms of a Hubbard language, and other features that are more naturally explained in terms of a quantum problem. So, I mean, the first thing, of course, which people working in the field of like strongly correlated materials or cuprates will point out is that we have a correlated insulator and we dope it and get superconductivity. This is a usual hallmark of the phase diagram of for example, high TC cuprate superconductors. Although, as I will show you, there is actually a way to get this in a quantum-model-like mode. However, the other features that seem more directly suggestive of a Hubbard-like physics are the fact that if you actually look at the charge in STM, you will find that the charge is really peaked at triangular lattice sites centered on something called the AA site in the Morey superlattice. So this is a Morey scale. But really, the very strong, the strongest indication of the Hubbard-like physics in the system is the fact that at intermediate temperatures, above the temperatures you see indications of ordering or correlated of ordering the system. You see that you have a relatively large entropy of a few kb per Morey unit cell. So that's kind of the strongest indication that there is a separation of scales between the point at which you get some kind of freezing of charge fluctuations, and when you get the eventual order. And this kind of pictures also that there's some numerical evidence in Monte Carlo studies and in some other numerical studies that really, if you simulate the system, for example, at charge neutrality, you would get ordering at some temperature scale, but you see features of a pseudo gap formation or charge freezing at a parametrically larger temperature scale. On the other hand, the system seems extremely close to describing a lot of the physics of a quantum problem. In particular, if you take a slight variant of the system where you align the twisted bilayer graphene with the substrate, I mean, I will not go into the details of that, but you find that you can actually realize integer quantum Hall states at zero magnetic field. And the idea here is simple, that you think that the system internally has an internal magnetic field, so it has these Chern bands that has a plus or a minus field, and when you add interaction of certain fillings, you tend to unequally fill the plus Chern bands or a minus Chern bands, so you generate a net Chern number. And you basically have to get a spontaneously generated quantum Hall effect. And they're usually associated with ferromagnetism, some orbital ferromagnetism. And there's also indication that in the system, you can get fractional quantum Hall states by applying a very small field. Of course, in any system, if you apply sufficiently large field, you would get fractional quantum Hall states. But typically, you get these when you apply a field that is comparable to a field needed to thread 2 pi flux per unit cell. However, here you can you get these fractional quantum Hall states at a small fraction of that. So, for example, at 1/10 or 1/6 of flux quantum per unit cell. There's also kind of a lot of numerical evidence from different methods, going from between like methods like mean field, which are maybe biased, but they also have DMRG and quantum Monte Carlo and many other numerical methods. And they have evidence for these ferromagnetic states and quantum-like states like quantum anomalous states, and also in some cases, or at least in some parameter regimes, also skirm.
Actually, yeah, this is really a naive question. The left figure is entropy.
Yes.
For mobile site.
Yes.
And the asymmetry around the new equal to 0 is there some?
The asymmetry.
Yeah, asymmetry.
Yeah, that's a very good question. I don't think there is a very good explanation. So most of the theory, like the most naive theory you can write is particle symmetric. You can add corrections to it that give you particle asymmetry, but usually the results you get are not as strongly particle hole asymmetric as the ones you see in experiment. So there may be some subtle effects that are not completely accounted for, and whether this is kind of a crucial aspect of the physics or a detail is not completely clear.
People haven't explored.
But no, but I mean, it's a known issue. It's not like, because, you know, particularly when you go at low energies, like superconductivity tends to occur only on one side. Correlated insulators are stronger on the other side. So it's not like something you can brush aside. But if you're thinking of a very high level of the kind of a framework to try to explain most of the observations, it could be reasonable to think of it as a higher order effect, but it also may be crucial.
And how is this entropy permeability side related to this figure on the middle in the density?
Yeah, these are kind of two different, they are kind of independent measurements, but both of them tell you that, so this tells you that this doesn't look, at least on a very naive level, it doesn't look like a quantum Hall system where the charge is uniform, that the charge is is strongly concentrated at some points in real space, while this is kind of, it's a different way to see that you have if the charge is concentrated, then you expect larger scale in the problem to be a Hubbard scale, so you get this separation of scales between ordering and.
So which phase is this? Which phase shows here? Which is what kind of quantum phase is this at the middle figure?
This middle figure, I think this is observed across doping ranges, so it's not specific to the specific like symmetry breaking phase. It's usually if you look at the charge density on a Mori scale, it mostly looks like this. I mean, there could be some density dependence, but it mostly looks like this. And you'll see this is a single particle feature. So if you have these 8 flat bands, if you take the charge distribution of any of them, you will find that it looks more or less like this. Of course, when you partially fill one band, you can be in a situation where you form some charge density wave on the Mori scale. But for most fillings, you get something that looks like this.
So it's not superconductivity phase. It's a
no. This is, and also this is typically at a larger temperature scale. But this is not for a specific phase. This is actually a single particle property. Okay. It's just if you fill a band completely, or if you fill it more or less uniformly in momentum and in real space, the charge distribution.
That's experimental data.
Yeah, that's STM. Yeah.
So it seems to suggest that the spin charge separation is a key feature of Hubbard model that differentiates with the quantum phase, and I want to try to understand why in the usual quantum problem there is no spin charge separation energy scale. So I think there are 3 energy scale like omega c, Landau-level gap, induction, and Zeeman energy.
Yeah, so I'm in the limit. I'm thinking in the limit where the omega c is infinite. And the Zeeman is 0.
Okay.
Yeah, so there's one energy scale.
So it's projected.
Yeah.
How should I be aware of the third figure? So the magnetic field.
Yeah. So okay. So this is magnetic field in Tesla. This is the filling, and this is a compressibility. It's a derivative of the
dmu over dn.
Of the dmu over dn. So usually a large, like a dark red feature means that you have an incompressible peak, and these peaks move in magnetic field. So this is it's known that if you have a Chern number, there's something called the Strata formula that relates the magnetic field at which you get the insulator, like the proper insulating filling with the magnet with the actual filling. So so basically. From this figure, you can, for every of these lines, the intercept will give you the filling of the parent state, and the slope will give you its Chern number. So these are all integer Chern states. Like this is, for example, here there is a 0. The strongest lines I think are 0, +2, and -2. But then if you look at the finer features like this white line and this white line, you find that they have a fractional slope, and fractional intercept, and this indicates that these are fractional quantum Hall state. But again, it's so yeah, I will not kind of discuss in a lot of detail this, because in the sense, in the picture I will present, the quantum Hall side will be very obvious. So the stuff that I would work kind of harder for is to show how in a topological band you can get something.
So how is the integer Chen number versus the fractional Chen number range and the different feelings? Are they behave in the different ways? So are there some features
You mean
like
particle?
nu 0, nu 1 versus nu 2?
Yeah. So here again, there is some not completely explained particle asymmetry, but there is an easy overall explanation, which is yeah, I mean this picture. Well, yeah, I'll show a picture in 1 or 2 slides. But so what you will find is that this system, you can really think of it as 4 Chern plus bands and 4 Chern minus bands. Okay. So when you and you know you're going from -4 to +4. So -4 means these are completely empty, +4 means they are completely full. So for example, if you are at and insulator means that you're completely filling a subset of these bands. That's something that is not hard to see. So if you are at charge neutrality, which is nu = 0, then you are filling 4 out of the 8 bands, and you have a few options. So you can fill all 4 on the same side. So then you get a Chern 4 state. You can also fill 3 and 1, and you get a Chern 2 state, or you can fill 2 and 2. Then you get a Chern 0 state. And you'll find that the main lines you see are 0, 2, and 4. So similarly, if you're at nu = 1, the options you have, you want to fill 5 out of 8. So you can do this, which gives you a Chern 3, or you can do this, which gives you Chern 1. So you'll see that the main lines at nu = 1 are either Chern 1 or Chern 3. There's more complicated lines that you need actually translation symmetry breaking to invoke, but the simplest and more prominent lines are explainable in this simple feature.
And so you get different types of fractional Chen number at a different feeling?
So the simplest ones to explain are the ones usually between 3 and 4. So between 3 and 4, you're basically, you have filled 7 out of 8, and you're partially filling the 8th one, and then you get the kind of simple like 1/3 states. However, at these other fractions here, you will get much more complicated possibilities, because you can have two bands at a fractional filling. So that's like the kind of states you get if you have a multi-layer quantum Hall system, and there you can get more complicated states like so-called Halperin states at other fractions. And I don't think I think in this paper there is a mapping of all kinds of fractions you get, but I don't think there is a good proposed candidate states for all of them. I mean, also in the sense that we don't understand really completely the energetics that picks this or that state.
Do you also get a non-abelian?
I think there is some even denominator fractions, but I don't know. Like it's in the paper. We don't know if these are. We don't really know if there are non-even states. So it's something that requires maybe further. But yeah, no, I wouldn't say we know for sure there's something on the video.
Okay, but something like abelian state.
Yeah,
okay.
yeah.
No problem.
But also it's all a finite field, so we can't get all like in this system you don't get all the way to 0. And it turns out that that's a feature. The fact that this system has features that are very non-quantum-like is what makes it kind of harder to get these quantum-like states. So you need to apply a small field to kind of push your system in the right direction.
I think.
So yeah, so I just want to briefly discuss a a model that was introduced with this main motivation in mind to try to explain how could a system have both features of topology, of band topology, and features of strong of fluctuating moments, so frozen charge of fluctuating moments. And one of the models that was introduced to explain this was a model from Song and Bernabeg that it's called the topological heavy fermion model. And in this model, the reasoning is, okay, we have a flat band. The flat band has topology. If we have topology, we cannot really find the basis of exponentially localized wave functions. So we cannot really describe this entropy free moment observation. So we need to invoke more degrees of freedom. We need to enlarge the Hilbert space. And we do this by invoking these remote bands. If we can mix the remote bands with the flat band wave functions, we can actually find proper linear combinations of them that doesn't carry any topology, which means that we can form a basis of exponentially localized form. And the way they phrase it is to say that once we mix these, we get a kind of an enlarged Hilbert space that has both local moments, we call F electrons, and itinerant electrons, which they call C electrons. And this model gives of course, I mean, you can ask under what condition do I want to mix with the remote bands? This is something you can always. This is just on this level. It's a basis change of the non-interacting model, but for interaction physics, usually the easy implications to deduce from this model is if you assume that the interaction scale U is larger than the gap to the remote bands. So in this case, it is really justified to mix the flat and the remote bands, and you naturally get local moments in this model. However, in the opposite limit, if you assume the remote bands are far, which is what we typically assume, usually when we think of a strongly correlated problem, we want to get rid of the remote bands, and we really think we're working in a restricted Hilbert space of the flat bands. Like, for example, that's related to a G's question that there's in the quantum problem, for example, there's a cyclotron orbit, and there is the cyclotron orbit, which judges provides the energy separation to higher Landau levels, and we usually, at least the first order, assume that this scale is infinite. I just introduced this model because to highlight that what I want to do is different. So I want to still maintain the idea that the physics is entirely described by the flat bands. I don't need to invoke any remote bands, which means I'm working in this limit. And in this limit, I have just an isolated band with topology, and it seems there is kind of no way around the topology argument that you cannot get any local moments in this system. So let me be more precise. So the question I want to ask is it possible for an isolated topological band to describe kind of the phenomenology of twisted bilayer graphene, which means it has this Hubbard-like features where the charge is concentrated at lattice sites, and where entropy, where there is an intermediate temperature scale with there's an intermediate temperature regime with a large entropy, but where order has not been established yet, and at the same time describe all the features of quantum Hall physics that I mentioned, like quantum Hall ferromagnetism, fractional quantum Hall, and possibly skyrmion physics. And this question is kind of important on several levels, because it's on a conceptual level, it's really a question of whether band topology places any strict limitations on interacting physics. Whether if I tell you this band is topological, can you have some kind of no-go theorem that you can never observe this entropy feature, or you can never observe a certain feature that we usually associate with these very local models. Of course, and also whether in an experiment this remote bands play an important role is something to be seen, but at least it's important to know whether some of the physics, some of the phenomenology is really sensitive to mixing to remote bands. Do we really need to invoke remote bands to explain, for example, the entropy observation? And actually, of course, the situation in reality is a bit complicated in the sense that the interaction and gap scales are of the same order. So of the two limits I said, where you take the interaction to be the largest scale or the gap to be the largest scale, it's not very obvious which one is more faithful to the physics, particularly since also the interaction and gap depend on the parameters of the problem. So usually in twisted bilayer graphene samples, you have different levels of strain, different levels of disorder, different angles, different gate screening environment, and these would change these values. So it's important to know what physics is kind of universal and what physics depends on a certain order of limits. And finally, since there's this whole side of the quantum physics that I still want to keep in my problem because a lot of the phenomenology is very easy to explain in this quantum language. So I want an approach that only retains the flat bands, because in this approach topology is manifest. I really don't want to. I really don't need to work very hard to understand, for example, quantum anomalous states or fractional quantum states or fermions. But obviously, in this approach, I'll need to work a little bit harder to understand this local moments formation or these free moments formation, if it is explainable at all. So just in summary, the typical regime where this topological fermion model is studied is this regime where the interaction scale is larger than the gap to the remote bands, while in this talk I want to focus on this regime where the interaction scale is smaller than the gap to the remote bands. And this regime is similar to the regime where we, for example, study usually the Hubbard model or the quantum problem. We assume that the gap to the remote bands is the hardest scale in the problem, and we just get rid of them. Yeah.
So for the topological heavy fermion model, and if I switch the order of U and delta,
yeah, I recover. I basically just I mean, you can get some maybe analytic expressions for the flat bandwidth functions, but you don't get this local moment physics because.
My impression is that their topological model, like the point is that the one-shot hydrophile can capture the renormalized band very easily. So will this feature change if the intention is smaller than?
No. So actually, one-shot hydrophile captures the renormalized band easily, even in the interacting BM model. So you don't need to go to topological heavy fermion model because. Okay, the main reason is that Hartree-Fock is exact for single particle excitations on top of a quantum Hall ferromagnet or a Chern ferromagnet can be computed exactly, and the exact result matches the Hartree-Fock. The Hartree-Fock is exact in this system in the strong coupling limit. So kind of any reasonable model you write to describe the model of this system will give you Hartree-Fock and single shot. Will give you the full Hartree-Fock from a single shot Hartree-Fock. Yes. So yeah, this is a feature also of interacting BM model. You didn't need to go to the heavy fermion basis to see.
Just make sure. So can I see the localized modes from the U1 larger than delta?
Yeah. So well,
what do I visualize? So
that's so. Well, first, I haven't really explained a lot about the topology, but the point is, when you look at these bands, you'll find that the topology is concentrated, like the Berry curvature is concentrated really around gamma. So you can kind of remove the Berry curvature by mixing it with other states around gamma as well. And if you remove the Berry curvature, so you can find them an admixture of the bands, which doesn't have any Berry curvature, and then you can form any localized wave.
So is it, on the left-hand side is the main motivation for there to have a U much larger than delta is because of the representation of the bands?
I think the main motivation is to explain, at least my understanding is, the main motivation is to explain local moments, to explain the entropy. So the entropy is suggesting that local moments in a flat band, in a topological band, you cannot describe local moments. So you invoke more degrees of freedom to describe the local moments.
And how do you see the non-local moment on the right?
Yeah, so on the right, well, I'll explain it a bit more, but these bands have, if you look at them and assume the right symmetries are there, then these bands have a Chern number, and which means that if you try to find any local representation by doing Fourier transform of the block states, you cannot find a representation that is better than power law localized. So in this sense, these have only non-local moments. Okay. Yeah. And yeah, I'll describe this a bit more.
Will there also be some experimental data, just like the one you showed? There's a density localized in some less real space honeycomb, is it?
It's triangular lattice.
But no, like a few slides back, there's some density yellow.
Yeah, there was this is a real space triangular lattice. So I will show you a cut where the density profile in the kind of model I will introduce matches extremely well.
That one is a real space.
Yeah.
And then that will reflect in, like, on the right will be sprayed or something.
No, that's a very good point that now I don't know if I'll get to it, but no, it's a very good point. So because of UV IR mixing in this system, or in a topological band, the concentration of the charge in real space will also give you concentration of the charge of the Berry curvature in momentum space. So both are concentrated at the same time, which is a bit counterintuitive to what you would think, that if you have a small scale in real space, you get a large scale in momentum space. Here you get a small scale in both.
You'll come back later.
Yeah, I should be able to get to it, but so I'll first explain what I've been referring to as band topology in twisted bilayer graphene. So usually when I zoom in on these two flat bands, I find that I have that the two bands are not featureless, that they are actually connected by two Dirac points at 2 points in the Brillouin zone. And just by looking at this figure, you would not realize it, but this band structure has something very unusual, which is that if you look at these two Dirac points, you look at the wave functions, you find that the wave function wind in the same way. That's very different from something like graphene. So graphene, just the original graphene, has also two Dirac points at K and K prime, but if you look at the wave functions, they wind in opposite ways. And in fact, that's a property that will be that's a property that will be true in any band structure produced from a local lattice model. Basically, if you have a band structure produced by a local lattice model, then the Fourier transform of the Hamiltonian in the momentum space would be periodic over Brillouin zone lattice vectors. So you have a Brillouin zone like this, and then you can look at the wave function as a spinor, and you can show that you can choose a gauge where the spinor is completely periodic. Which means that if the spinor winds clockwise at this point, it has to wind counterclockwise at the other 0 point. So you have two direct points. However, if you look at this band structure, you find that the spinor winds the same way, which means they cannot be described by a periodic wave function in periodic and smooth wave functions in momentum space. And that's mainly a reflection of the topology that if you cannot find periodic and smooth wave functions in momentum space, then their Fourier transform would not be exponentially localized in real space. But the way I want to see it is the following. So usually when we think of a one-band system, we define some Berry curvature, but here the projection on the lower band or the upper band is ill-defined because they touch at 2 points. So I should characterize the topology in this system using a non-abelian Berry curvature, which is it's a 2x2 matrix generalization of the Berry curvature. And the important property is that this Berry curvature is odd under certain symmetries, in particular the combination of twofold rotation and time reversal symmetry. And this means that in a certain representation of the symmetry, this Berry curvature is proportional to one of the Pauli matrices. For example, in the standard representation of C2T, this should be proportional to sigma y. But what this means is that I can choose a different basis to represent this problem, particularly because the energy basis is not very meaningful. The blend is extremely flat, so this non-interacting energy scale is a very small scale. So I can choose whatever basis of these bands I want to describe that is convenient for the interaction. And that basis turns out to be the basis that diagonalizes this non-abelian Berry curvature. It's usually called sublattice basis. So in this basis, I find that I can rewrite these bands as one Chern plus one band and one Chern minus one band. And the single particle dispersion would appear in this basis as a tunneling between the two bands, as a single particle tunneling term between the two bands. And because this is a small scale, I can, at the first approximation, I can ignore it. So what I get is, of course, this is pictured in one valley, or one flavor, one valley, and one spin. The full picture would be 4 copies of that. Where so my whole problem is 4 copies of Chern plus one band, Chern minus one band that are related by some symmetry, actually C to T symmetry. And there is a small tunneling terms that connect them that I can switch off at the first approximation. And the main part of the interaction is just the Coulomb or whatever density-density interaction projected onto these bands. And the whole information about the band topology comes because when I project the interaction, I get this form factors, which give me the overlap of wave functions at different momentum, silver wave functions at different momentum. So you can ignore this part and just look at 4 plus 4 with some interaction that is projected on these bands that knows about the wave function. So because a flat Chern band is almost a Landau level, this picture already is suggesting a very kind of Landau-level-like picture. It turns out that that's not all of the story, because the Landau level has an extra structure that turns out to be very important for the many-body physics, and that extra structure is a holomorphic structure. So if you look at the wave functions of the Landau level, you find that you can always write them as some holomorphic function of z, and z is x plus iy. So this is psi n. This labels states within the Landau level. And this is n, and this is multiplied by some function of x and y. This itself is not a holomorphic function, but it's common to all of the bands. It's common to all of the states within the same Landau level. So it turns out that the Chern bands you get in the system are also close in some sense, or can be close in some sense to possessing this holomorphic structure of Landau levels. Yeah.
Yeah, since you switch slides. Okay, so when you say non-abelian Berry curvature here, just means multi-band.
Yeah.
And here just 2 bands. So
yes.
Okay. But the Chern number is still even integer here. It's integer.
Yeah. Well, because so what I do is I do non-abelian Berry curvature and I go to a basis that diagonalize it, and there is a basis that diagonalizes as k independent. So I can really transform the basis and go from non-abelian to abelian Berry curvature. It's just I need to choose the right basis. So since
you have a Hubbard.
in the interest of time, I will not go in detail in these ideas, but that as a result of studying this problem of interactions in a topological and a flat topological band, many people, including myself and people in the audience, like G, been thinking of what is the essential features that make a lowest Landau level. And it turns out there is a way to think of this structure, the holomorphic structure of the Landau level, in a more kind of general and abstract language, by saying that we define something called an ideal or a vortexable band as a band that where I can define a complex variable x plus iy, and if I multiply the complex, if I multiply this z by any wave function of the band, I don't get out of the band. So if I multiply by z and project it onto the band, it's the same as if I don't project into the band. So I don't get any component out of the band filters. And it turns out that this, for example, for these fractional quantum states like localized state, this is really the crucial property. So people have known for some time that there is a so-called pseudo-potential arguments, which tells you that if you have short-range interaction, you can actually show that the exact ground state at certain fillings is a Laughlin state, Laughlin-like state. And you can also do a similar version of this argument for other more complicated states. And it turns out that just using this property, you can generalize these arguments. So you can show that the exact ground states for short-range interactions are Laughlin-like. And another result that it turns out also to be interesting about the system is that you can also make exact statements about skyrmion, or what I call here spin polarons. So spin polarons and skyrmions are roughly the same thing, just spin polarons have a well-defined SZ quantum number, while a skyrmion is a coherent superposition of them, so it doesn't have well-defined. But using this same structure, you can actually solve for excitations on top of the ferromagnet exactly, and show that they are actually that these skyrmions are the lowest energy charge excitation. So you can make so this structure allows you to go beyond topology and make very sharp energetic arguments. And of course, the one of the first realizations in the study of twisted bilayer graphene was that there is a certain limit of the description of twisted bilayer graphene called the chiral model, where this ideal or vertexable limit is realized. And a very nice result by G showed that you can generally think of these ideal or vertexable bands as Landau levels, pure Landau levels in a non-uniform magnetic field, and he proved that very generally the wave function for any ideal band can be written in terms of the wave function of a Landau level up to some charge modulation. So this is a periodic function that basically modulate, like instead of the Landau level, which has a very uniform charge, here you introduce some charge modulation. And yeah, you can relate this charge modulation to an effective non-uniform magnetic. So this whole story tells you that there is a sense in which you can understand these flat topological bands. You can relate these flat topological bands to Landau levels, not only on the level of topology, but on the level of energetic. And of course, it may or may not happen that the actual system is close to this limit, but it gives you a handle to measure kind of how close you are to a real Landau level or quantum system. And here I will just, in one slide, I will review, maybe this is work from like 2 or 3 years ago, of if you just put all these ingredients together and add strong interaction to this system of opposite tunnel coupled Chern bands, what kind of physics would you get? And for simplicity, I'm just including 2 out of the 4 bands in each Chern sector. So the first part is something I already kind of explained on the board, which is that you can prove in some cases exactly that the correlated insulators in the system at integer fillings are some generalized version of quantum ferromagnetism, in the sense that you can show that the projected interaction I wrote as it's the exact ground state, or at least exact eigenstates at integer filling states where a subset of bands is completely filled and the rest is completely empty. And these are proper generalizations of ferromagnets. And this already gives you something that matches one of the phenomenological observations, which is that what I was also explaining here in response to Jubin's question, which is that at even integer fillings, this gives you a correlated insulator that have an even Chern number. So it may be a quantum anomalous full state. It also could be a kind of a trivial insulator that doesn't have any quantum Hall response. But at odd integers, you always get odd Chern number, which means that odd integers, you always get quantum anomalous full state. And at least phenomenologically, the quantum anomalous full states are always seen at odd fillings. And this picture also explains, these kind of lines that were in the figure I showed earlier. So we can really look at what integers or what slopes do these lines appear, and they would match what you would get from this picture. Since I want to get to other stuff, I don't want to go into this part in detail, but you can actually show that if the charge carriers in each of these Chern sectors are skyrmions, you can show that they have a pairing. They have a tendency for pairing. So this is a model that, although it's motivated by quantum Hall problems, which usually don't have pairing, but here because we have often Chern sectors related by time reversal symmetry, we can get pairing, and there's a model where you get pairing very naturally. So basically, you have a correlated insulator at certain integers, and you dope away from it and get superconductivity. And also, in this model, you can get fractional quantum anomalous solid states in certain at fractional fillings. So from this picture, you kind of naturally get a lot of the physics of the system, but not everything. So the main part that still is not very clear how to reconcile with this picture is this charge concentration at A. Of course, since we use the wave functions obtained from the Bistritzer-Macdonald model, and Bistritzer-Macdonald model already knows that the charge is concentrated, but this is considered kind of a quantitative feature. It's not an important conceptual ingredient of this strong coupling kind of quantum Hall motivated picture of the physics. And in particular, it's very puzzling how would you be able to analytically understand the emergence of free moments at some intermediate temperature scales, because if our picture thinks of the system as just some copies of a quantum Hall system, we know that if we only have the interaction scale in the problem, then the interaction scale will control the exchange scale, which any basis of wave functions, of local wave functions we have, will have very large overlap. So at whatever scale the interaction sets in, we should freeze both charge and spin, not have this weird separation of scales between the scale at which the charge is frozen and the scale at which order is established. There's also some other detailed observation, for example, that if you actually add strain to this system, and it is typically strain, you can get competing states that are spirals rather than ferromagnets. And this is being seen both in numerical Hartree-Fock and more recently in experiment. So in experiment, we know that there is an instability away from these ferromagnets to spirals when the sample has even an intermediate level of strain. And of course, you can say that strain is it's something that changes the physics, so you get into a completely different regime. But the question is, again, if the largest scale in the problem is an interaction scale, and this interaction scale picks a ferromagnet almost uniquely, how would you get different competing states by applying a relatively small perturbation like strain? So it seems that the energy scale that protects the ferromagnetism is much smaller than you would naively expect. Yeah.
It was a very simple question. How does the strain reflect itself in the change of the microscopic parameters of the system?
Yeah, so the strain could indirectly change a lot of the microscopic parameters, but its main effect is just it changes the dispersion a little bit. But the main effect is that it breaks a threefold rotation symmetry. So it couples to orders that break threefold rotation symmetry much strongly. And
in your ab initio description of what you're doing in the system, if you have a strain, which parameters do you change?
Yeah, so you take, I didn't write kind of the microscopic model. So usually in the description I have, there's what enters the interaction of the wave functions, right? And the wave functions come from some single particle model that's usually takes two Dirac cones with some more coupling. Now strain will modify these terms, so like it does in graphene. And the important strain is usually heterostrain, which is different between layers, because that's an effect that's magnified by Morey, rather than homostrain that's the same for both layers. So it's uniaxial heterostrain that is the important one.
Actually, just
Yeah.
I just try to read the data more carefully. So this middle figure is the different versus the twist angle.
Yes, so this is a cut, this is a cut from here to here at different twist angles.
Okay. And
So it's a peak, there's a peak at this little AA and there's a. Basically everywhere else is very small, but there is a problem, there's a dip where this is, I think, this needs to be zero here by symmetry, but overall it's very small away from A.
okay, so what's the kind of middle peak at the SP implies?
Well, it's just the symmetry, the symmetry tells you that at these points you'll have either a peak or a dip because of you know, it tells you the extremum of this function will occur at these high symmetry points. And I think there's another symmetry reason why it has to go to zero at this point. So
That means there's some density concentrate at SP.
but this is, I mean, this peak is a lot smaller than this peak is like an order, almost an order of magnitude smaller. So really all the density is in here.
Okay, but it doesn't. There's nothing.
Yeah, I think I don't think actually it turns out that the standard model for describing this system, like a Bistritzer-Macdonald model, doesn't reproduce this peak very strongly, like as strong as it should be. But yeah, it will not play an important role.
Thank you.
Yeah, so can briefly summarize question at this point? If I understand correctly, the point is that experimentally observed the separation of a couple of energy scales that are emergent equilibrium. In your setup, you have focused on the projective problem, and you don't have enough energy scales to reflect that's the motivation.
Yes.
But can you summarize what energy scale in your problem? Like the first, there is a bandwidth. Second, there's induction.
Yeah. Let's set bandwidth to zero.
Oh, you set bandwidth to
Yeah.
but not induction.
Yeah.
But Berkeley standard deviation is also energy scale.
Yes, that would be basically the way to introduce more scales in this problem.
Okay.
So yeah, so you kind of anticipated the resolution. Yeah.
Okay.
Yeah. So just before I kind of present the full resolution to how to explain these observations in a model of topological bands, let me first kind of discuss why discuss in more detail the argument for not being able to find the local basis of a topological band. So this is related to the notion of called Wannier obstructions. So the idea is that Wannier obstruction means that we have no basis of symmetric and exponentially localized orbitals to describe a given band. And phrased in this way, this is a kind of a binary statement. It just tells us either we have an exponential basis or we don't have an exponential basis, but we can make this more quantitative by realizing that actually this statement stems from the fact that if we have a Chern number, for example, we cannot choose a smooth and periodic gauge for the block wave function. When we try to make their Fourier transform to get a Wannier basis, this Wannier basis cannot be exponentially localized. So there is kind of a simple exercise you can do, which is what we showed here is that you can always choose the gauge singularity for a Chern C band to have a specific form. And from this, we can actually deduce the asymptotics of these Wannier functions. So we can make a sharper statement about asymptotics. It was already known that asymptotics should not go should go at least as 1 over r squared, because that's the only way you get a finite Chern number. But by this gauge choice, we can show that the asymptotics not only go as 1 over r squared, they encode the Chern number in the winding, but most importantly, they have a universal prefactor, numerical prefactor. So in the sense that no matter what you do inside the Chern band, there is the tail of the wave functions in real space is universal. You cannot make it small. So you cannot naively make this overlap between wave functions that give you this this ferromagnetic exchange scale. Naively, it seems you cannot make it very small. So yeah, there's power law tail. However, there is a loophole to this argument, which is that when we actually compute this exchange, we don't. What we employ is the whole integral of the tail overlaps of the wave function, not just asymptotics. Yeah.
Sorry, then does that imply that you have long range hopping in this subband or?
Yes. So I mean, at this point, since I don't have hopping, I'm projecting the interaction. Yeah, I will have a long range ferromagnetic interactions. And if the tail is O of 1, these long range interactions seem like they should also be O of 1. So they are large, very large long range ferromagnetic interaction. However, if you really try to compute this exchange integral, what matters is not just asymptotics of the tail. It matters the whole weight inside the tail, which means it also matters where the tail sits in. And I will show you that if I incorporate this charge concentration in a natural way in this model, I find that although the tail is universal, there's a new length scale in the problem related to the concentration of Berry curvature, and only at this very long length scale this tail sits in. So what would happen is that you have Wannier functions that have a very strong peak in the middle. They have an extremely shallow tail, and only at the parametrically long length scale these would match the power law. And by having this new length scale, I can kind of reconcile the fact that the tail has to go sufficiently long distances as a power law, and the fact that the charge can be very strongly concentrated. And importantly, because this tail is 1 over r squared, if I compute some transport quantity, which usually have they have expectation values that include the r operator, even if the weight in the tail is small, the transport quantity will be sensitive to just what's in the tail, the asymptotics of the tail. While stuff like the exchange overlap will be sensitive to the whole weight in the tail. So I can make the weight small while maintaining the topological properties that ensure I get the right transport. For example, that sigma xy, like the Chern number in this band is 1, it's O 1. It's not parametrically small. And this would appear maybe in 2 slides.
You should take your time.
Yeah.
12 you still have about 40 minutes.
Yeah, okay.
Take it. It's recorded, everyone will be better.
Yeah. So what I yeah.
Water.
Oh.
Take it back.
So what I want now is to kind of think of the minimum of ingredients I wanna use to describe the physics. And some of these ingredients I already described, which is this band topology, this opposite set of Chern bands that are similar to Landau-level. But I also want to incorporate the charge concentration in a more kind of serious way in my model, like as a qualitative part of the character of these bands, rather than just the bandwidth function happened to have this charge profile. And of course, if you want to really do some detailed energetics at low energies, this model suggests that you have some U4 or U4 times U4 symmetry, but the actual symmetry is smaller, it's U2. So you need to include these kind of symmetry breaking terms. And also, if you want to incorporate strain or incorporate other terms. But on the highest level, we want to think of what would happen if we have a topological band where the charge is concentrated. I just will input these 2 pieces of information, and I'll try to see what would happen. So the simplest way to do this is to just take a band wave function that has the right symmetry and the right topology, and just multiply it by a factor in real space that concentrates the charge at 1 point. And this form is kind of, in a sense, motivated by the nice result from G, where he said that any ideal band can be written as a Landau-level wave function times a modulating factor in real space. Here, I'm not really assuming this is a Landau-level wave function, just assuming it's some wave function for a band that has the right symmetry and topology, but I'm not really assuming anything else. But then I'll take this parameter lambda that controls the concentration of charge to be large. And that would give me a band where the charge is concentrated in a region, in a small region in real space. So I get a model that has a small parameter, small control parameter, which is called S. Now, now clearly from this procedure, in the limit of very small s, only the vicinity of only the value of this psi k of r at r equals 0 matters. Now, if this band is topologically trivial, then generically I can assume that psi k of r at r equals 0 never vanishes for any momentum. So I can really take the limit of s going to 0 and get a delta function. And in this case, I will just get a type binding model. And of course, the type binding model then will be incompatible with the Chern number. So what would happen if this band has a Chern number? If the band has a Chern number, it means that if I look at the wave function psi k of r, then the wave function will have a 0 in real space, but this 0 winds around the unit cell as the momentum k winds around the Brion zone. And what this means is that I cannot really take the value of psi k of r at r equals 0 for every k, because there would exist a k at which psi k at r equals 0 is 0, and the wave function would be not normalizable. So at this points close to the zeros, I need to expand the wave function to next order. And from this, I get kind of a universal form for the wave function in a topological band that has, or like in a Chern band that has a concentrated, where the charge is concentrated, controlled by control parameter s in the limit of small s. So it turns out that this universal form, if I impose all the symmetries of twisted bilayer graphene, it only depends on one extra parameter. So there's this small parameter, and then there's this extra parameter that's of order 1. You can really think of this parameter as the speed by which the 0 moves in real space as k moves in momentum space. So it's a parameter that relates real and momentum space.
So D is the holomorphic candidate?
Yes, yes.
So this result is derived under what conditions, like a smooth gauge or?
Actually, I think this is not a smooth gauge because there's a singularity at k equals 0.
So it's a periodic wave function.
Yes, yes.
But what if I choose the gauge to be quasi-periodic but smooth in the above? Can we get the same result?
Well, I think the wave function may look different, but at the end of any gauge invariant quantity will be the same. So for example, the form factors are not gauge invariant, so they will look different. So there's some gauge transformations that relate to 2, but at the end, if you compute the Berry curvature from them, it will be.
So what's the motivation to choose in the singular gauge?
I think because we want the form factors away from this singular point close to k0 to be 1. So that would be the same as the form factor in Hubbard-model. So it makes a lot of things easier. So from this wave function, you can actually get already a lot of single particle information about your system. For example, you get actually analytic expression for the form factors, the charge distribution in a band, and the Berry curvature. And one important, well, I'll show you these expressions now, but one important feature I want to highlight is that because of the topology of the band, because of the Chern number, there is actually, this band has UV-IR mixing, which means that introducing a small length scale in real space also gives us a small length scale in momentum space. And so when we concentrate the charge in real space over an area S or S squared, the Berry curvature also gets concentrated in momentum space over an area that's proportional to S. This beta parameter is of order 1. And and these S and beta parameters, they are kind of were derived in very kind of general grounds, just general phenomenological grounds, but you can fit them to the Bistritzer-Macdonald model, which is the model that describes the single particle physics. And you can see that you can fit the charge distribution and the Berry curvature extremely well using just these, by introducing just these 2 parameters. So, Gene, this gets back to your question. So, you see, this peaks is still here, but it's not in the theoretical description is not as common.
So this, the correlation between the charge distribution and the Dirichlet distribution is a feature of trim band only, or also applied to trivial band?
No, in trivial band, you can the Chern number can be zero everywhere, while the charge is a delta function.
So this is a feature of trim.
This is a feature of Chern band. Actually, it's a bit more if the Berry curvature is if the charge is concentrated at 2 points, then you can get uniform Berry curvature. So it's a feature of having all the charge concentrated at 1 point, all the Berry curvature are concentrated at 1 point, and the way you understand it is, if all the Berry curvature is concentrated at a point, that's a 2 pi flux. Now, if you put your system on a finite size, that's you have a grid, and if your grid is sufficiently fine, if the grid size, the grid squares are sufficiently big, you'll not be able to detect the 2 pi flux. So this means that there is a long energy scale at which you can only at which you can see the topology. But that's a feature specific to having all the Berry, like a 2 pi Berry curvature concentrated at the point. If your Berry curvature is split between 2 points, and each of them has a pi, you'll still be able to know it is there even away from that. So there's something unique about having the charge concentrated at a point, the Berry curvature concentrated at a point.
So the number must enter in certain ways.
Yeah, here just assume Chern. In higher Chern, I think you have to decompose. You use the decomposition into different Cherns, and then you do it for every band separately. So this model just shows you that, these are full functions, and I'm fitting them on just 2 parameters. So it tells you that this is kind of the right picture in the sense that I can fit the microscopic model using this kind of phenomenological wave function, or just a very simple idea that I take a wave function with the right symmetry and topology and just concentrate the charge. But and also I just want to mention that you can fit this ideal band or vertexable limit ideas into this form. It turns out that if you do this procedure for an ideal band, you always get this beta equals to 1, because basically momentum space and real space are tied. And this, in a sense, also gives you a way to write a model that is basically a quantum Hall Landau-level quantum Hall problem. So sorry, Landau-level problem with concentrate, which also incorporates that aspect of charge concentration, and that's quantitatively much more accurate than the chiral model for twisted bilayer. So the chiral model, you see that it gets some features very inaccurately, like the Berry curvature concentration in the Bistritzer-Macdonald model is way more concentrated than in the chiral model. But using this ansatz, I can actually write a model that is vertexable, that is ideal, but that has very good charge distribution, the very good match to the actual charge distribution, which also tells you that these vertexability ideas are not irrelevant to twisted bilayer graphene, even in its realistic limit. It's just that the chiral model was not a good description of this realistic.
Well, chiral model is vertexable. It means that the chiral model is not concentrated enough.
Yes, something related. Yeah, I can just, so I take a chiral model and concentrate things, I can almost match these. But you can already see that, since I have one fitting parameter, I can either match very well the Berry curvature, but I'll get to some slight deviations in the charge distribution, or vice versa. But it tells you that there is no fundamental tension between vertexability and the basic phenomenology of the BM model, how the charge and the density distribution flow.
I'll just make sure. So the figure on the right is the Berry curvature. The horizontal axis is also the same as the one.
No. This is yeah. So the Berry curvature. This is some cut in momentum. This is some cut in real space.
Oh.
So as you already anticipated, because we have a model where the charge is concentrated and the Berry curvature is concentrated, we have this extra small parameter, which allows us actually to define new energy scales in this problem. So in contrast to other interaction-only problems, like in the, if we just take the Landau level projected interaction in the limit where the bands are flat and the other bands are remote, then this problem has only one interaction scale, which is a Coulomb scale computed at as the magnetic length. If we also take the Hubbard model when we switch off the dispersion completely, which is its flat band limit, we also have one scale, which is U. However, in this problem, because we have the small parameter, we can define several energy scales. So there is the Coulomb scale, which is Coulomb evaluated on this scale of the Mori unit cell. But then we can define a scale associated with the Coulomb interaction, but evaluated on a much smaller distance, which is the distance at which the charge is concentrated. So that's a parametrically larger scale than the Coulomb scale. And this is the scale that would usually be associated with the Hubbard scale, because it's the interaction projected onto the small region where all the charge is concentrated. But then we can also define a parametrically smaller scale that turns out to control the ferromagnetic exchange, which is S times the Coulomb scale. So this is smaller from the Hubbard scale by a factor of S squared. And this basically is the kind of the resolution of many of the issues I said at the beginning. So this is already a model that has parametric separation between the exchange scale and the Hubbard scale. And you can see this in a very kind of concrete way if you try to compute, you just take a ferromagnet with these wave functions and compute the spin wave excitations on top of the ferromagnet. So this is what, and this is related to the actual ground state of this model, because the actual ground state of this model are known to be ferromagnets. So here I'm taking a value of S that's reasonably large. And then I'll make S smaller and I'll see what happens, how this spin wave spectrum evolves. So as I make S smaller, you see that, what happens is that this branch, which is mainly controlled by the exchange scale, it goes down, which means that the energy gap that protects the ferromagnet gets much, much smaller. And this kind of explains why you could get these spiral instabilities when you slightly perturb the system. And the rest of the spectrum is actually, if you think in terms of real space or a Hubbard picture, the rest of the spectrum is associated with the double optics. It's creating an electron hole, a spin flip, but it's split into an electron hole that sits on different sides, and this creates a double occupancy. And this, you see that it grows as I reduce S. So this gives you this other energy scale. So that's one way to see the separation of scales. There's also, you can see how the resolution to the kind of Wannier function dilemma. How do you reconcile a 1 over r squared asymptotics at long distances with having most of the charge concentrated in the main unit cell? And in this model, this happens very naturally because you have this extra energy scale, extra length scale, 1 over S. And you see that this universal tail asymptotics only set in at distance 1 over S. And this allows for most of the weight of the wave function to be within the unit cell. So this is the weight of the wave function inside the unit cell is of the order, deviates from 1 by a factor of S squared. We can see it here. So you have this huge peak in the main unit cell, and then you have a kind of a very shallow tail that only approaches asymptotics long distance. But it's important to note, which, as I said earlier, that this tail is associated with some momentum space singularities. So it's not really a perturbatively small effect. I cannot get rid of it. For example, if I want to compute any transport quantities, I usually apply derivatives. So the current operator momentum space, which acts as a derivative, and taking a derivative to an object that has some singularities in momentum space magnifies their effect. So they could lead to the main contribution to transport, although they are negligible contributions in the phase space sense, that they're singularities that are limited to very small regions in phase space. And since kind of one of the motivations I showed earlier was entropy, so it would be nice to see that how this model could reproduce the entropy observations of experiment. And so this model now, as I said, has two energy scales, one associated with U and one associated with this US squared. Below the scale U, you basically freeze the chart in the sense that you put the chart into these Wannier functions that has power law tails. But because the power law tails, their overlap is parametrically small, if I'm in this temperature window, I can just ignore the existence of the tails, and I basically get free moments, although they are free non-local moments because they have these power law tails. And only at this parametrically smaller scale I get the order. So if I'm here, I can actually rigorously compute the entropy up to order S squared correction. Now I have a control parameter that I can compute quantities up to certain order in this quantity, and I get this expression for the entropy. Actually, this is a rigorous inequality, but if I'm at this intermediate temperature, I can just ignore this term, and the result I get looks something like this. So that's already kind of similar, or at least like it's the right shape and the right overall energy scale as the purple figure, which is the highest temperature range of this entropy data. However, you see as the temperature lowers, we see this dip that happens at charge neutrality, and it turns out that is due to strain. So when we include strain, it kind of freezes the entropy in some directions, and the way it freezes the entropy is actually filling dependent. So, so if we introduce a strain such that the strain scale is, of course, smaller than the biggest energy scale in the problem, which is the Hubbard U, but it's larger than this other exchange scale. Well, it needs to be larger than exchange scale, otherwise it will not stabilize spirals on top of ferromagnets, because ferromagnets are protected by the exchange scale. So we can repeat this calculation and basically thinking of the strain as some Zeeman field in some direction in this large, these moments are like U8 moments. So it's a very large space, and strain acts as some Zeeman field in that space that picks a certain direction. And it turns out that neutrality picks a unique direction. Away from neutrality, it picks a direction with some free rotation around it. So as we have some intermediate strain and we sit here, we find that we get actually this figure, which looks a lot like the blue figure. So as we lower the temperature, we will evolve from this region where we get this figure to this region where we get this figure. A very interesting consequence of this picture is the following. In the Hubbard model, when we look at what happens in this region, we say that the charge is completely frozen. So this is an insulator. And then spin fluctuates. This is how I get the entropy. However, here there is a subtlety, which is that we're still freezing this like having this local moment, fluctuating moment phase in a band that is topological. Because the band is topological, it has to have at least some whole response. And this has to come from somewhere, and the somewhere is the kind of these singularities in momentum space that gives you these tails. And as we said, these singularities can be ignored when we compute something thermodynamic, because we are averaging over the whole phase space. But if we are computing something that is k-dependent, that cares about the transport, this is not necessarily the case. So if we try to look at this fluctuating moment phase, we'll actually find it's not an insulator, but it's semi-metal. And one way to understand this is that when you order these fluctuating moments, if you order them ferromagnetically, you get an insulator. But if you order them into some spiral, turns out you get a semi-metal, or you get something that is gapless. And what this Mott phase is really a thermal average of all the possibilities to order these fluctuating moments. So it turned out at the end that phase is a semi-metal. And we can kind of show this more or less rigorously by just computing the spectral function. And again, using the fact that these singular features that capture the topology only sit in a very small region in phase space, actually allows you to simplify all the diagrams that contribute to the self-energy in such a way that you can show that any diagram that contributes to self-energy is related to a diagram computing the self-energy in the Hubbard model up to an overall factor that is singular small k. So if k is larger than this factor of s, this factor doesn't matter. And we expect to get the same spectral function as in a Hubbard model, which is one band at plus u and one band minus u. But if k is close to close to 0, it's closer than 1 over s to 0, this factor will give us a new feature. This feature is actually a quadratic band touching. So at this intermediate temperature range that is above the ordering temperature and below the gap, we get a Mott semimetal. It's a kind of a new type of Mott phase that is semi-metallic because it forms from bands that still know about the topology. So what this is saying is that this model is not just like our model where we can take this S to 0 and ignore the effects of the topology. It really depends on what observable you're looking at. So if you look at the thermodynamic observable, where you average over momentum space, the small region of momentum space which has a singularity doesn't matter. But if you compute something that knows about the k-space structure or that knows about the transport, these small regions in k-space will make a difference. So it will make the difference between being an insulator and being a semimetal. So in conclusion, I've introduced this phenomenological kind of way to think about the flat bands of twisted bilayer graphene in such a way that I could write a universal wave function that only depends on that only relies on very few observations, particularly the symmetry and the topology of the system, and the fact that the charge is concentrated. And I showed you that. Well, first, this model is analytically tractable in some sense because it has a small parameter, and it naturally captures kind of most of the important aspects of physics, like topology and geometries, in the sense that we can go to an ideal band limit. It can capture these kind of strong coupling flavor ferromagnets that are naturally understood from a quantum Hall perspective, but also it can explain the formation of decoupled moments and the entropy at intermediate scales, and just this whole phenomenon of the separation of scales in an interaction-only mode. And importantly, this doesn't really require invoking the remote bands. So at the very least, it seems there is a way to explain the phenomenology without the remote bands. Maybe the remote bands are needed to do some things quantitatively, but this is suggesting that at least some of the broad features do not require remote bands. And I just want to emphasize the model has a small parameter, but it's not perturbatively related to our model. This limit S to 0 is singular, and this singular limit is where actually all the interesting physics is hidden. That's the end of my talk. Thank you.
So it seems that the semimetal is logically protected.
Yeah. Yes, I mean it does come because the bands are topological. The only way you can get a Mott phase is by doing this trick and so get to get it as a semi-metal, not a full insulator. Yeah.
So there's kind of no-go theorem.
Actually, yeah, I would like to phrase it as a no-go theorem. I think there should be, but so earlier, like if you asked me 2 or 3 years ago, I would have said that there is a no-go theorem that tells you cannot get a Mott phase in a topological band. But this seems to be like a proper Mott phase, but it's just not a Mott insulator. So maybe there is a statement you can make that you cannot get a Mott insulator no matter what you do. That it has to be semi-metallic and that the semi-metallicity is protected. And it makes sense because it's you still need to get the right sigma xy. So it would not be a complete Mott insulator, but But okay, this is slightly different because it tells you it cannot be completely gapped. It's a semi-metal, so it's a bit stronger statement.
Look at the zero or four properties of the green function.
So I mean to prove the
Linear surface.
okay. You think. So what do you want to show?
So no, for liquid there is a material theorem.
Yeah.
But for molten solid there is a material surface as well.
I see. Yeah, so I think that's a good idea. Maybe by looking at that, we can prove some no-go theorem. If that's true.
It's something topological but not physical.
Yeah. Other questions?
Questions, comments? Yeah. But no, we should say some again, and you can still stay to ask questions. Thank you.